Welcome to The Explainer. Today, we're talking about a technological leap so huge, it doesn't just make things faster, it completely rewrites the rules of how we solve problems. Okay, let's just jump right in with something that sounds like it's straight out of science fiction. Get this, a calculation so complex it would take the world's most powerful supercomputer 47 years to finish? Well, Google's quantum chip did it in just a few seconds. Yeah, you heard that right. Years versus seconds. So you might be thinking, okay, it's just a faster computer. But it's not. This is way bigger than that. We're talking about the dawn of a totally new age of computing, a fundamental shift in how we can even think about solving the world's hardest problems. For decades, all of our computers have been based on simple on or off switches, ones and zeros. But now we're moving past that. We're building machines that don't just follow simple logic, they actually harness the weird, powerful, and fundamental laws that govern the universe at the tiniest scales. Now, this didn't just happen overnight. This incredible leap forward is actually built on a journey that started more than 2,000 years ago. And to really appreciate where we're going, you gotta understand how we got here. Think about it. Our mission to compute started with actual physical gears in ancient Greece. Then it evolved to these giant steam-powered mechanical engines. The first true revolution was the transistor, which let us control electricity. And finally, we figured out how to cram in an entire computer onto one tiny little sliver of silicon. Each one of these steps was a massive leap. And for the last half-century, our progress has been almost predictable, thanks to one guiding principle, Moore's Law. The idea was simple. Just keep shrinking the transistors, cram more of them onto a chip, and boom, your computing power roughly doubles every 2 years. But here's the thing. We've kind of hit a wall, a literal, physical wall. When your components get down to the size of just a few atoms, the normal rules of physics just stop working reliably. Electrons start doing this bizarre thing called quantum tunneling, where they basically just teleport through solid barriers. You just can't shrink them anymore. So if we want to keep moving forward, we can't just keep playing by the old rules. We have to throw out the rule book and embrace a whole new one. We have to learn how to speak the universe's native language, quantum mechanics. And in this new language, the basic letter isn't the bit anymore, it's the qubit. And a qubit is the fundamental building block of a quantum computer. It's often made from something as small as a single isolated electron. It's basically a computer bit with superpowers. And this is where things get really weird, but also really cool. A regular bit is like a light switch, right? It's either on or it's off, a 1 or a 0. Simple. A qubit, though. A qubit can be both on and off at the exact same time. It exists in this sort of cloud of all its possible states at once. This mind-bending property is called superposition. The best way to think about it is like a spinning coin. While that coin is spinning in the air, is it heads or tails? Well, it's neither. It's kind of both. It's in a state of all possibilities. And that's what allows a single qubit to explore a whole bunch of different calculations all at the same time. And this is where the power just goes completely off the charts. It's not linear, it's exponential. With just 100 qubits working together, you can explore more possibilities simultaneously than there are atoms in the entire known universe. Just try to wrap your head around that number. It's almost impossible. And then you add another layer of quantum weirdness on top of that, entanglement. Imagine you have two coins that are magically linked together. If you flip one and it lands on heads, you instantly know the other one is going to land on tails, even if it's on the other side of the galaxy. Entangled qubits have this spooky connection, and it lets them work together as one giant, powerful team. So this all sounds incredible, right? But as you can probably imagine, trying to build a machine that controls the universe at this tiny, fundamental level, well, it's one of the hardest engineering challenges humanity has ever even tried to tackle. The number one enemy here is something called quantum decoherence. That delicate quantum state is so unbelievably fragile that the tiniest little vibration, a stray bit of heat, even a stray magnetic field, can cause the whole calculation to just collapse and vanish into nothing. To even have a chance of fighting this, we have to create one of the most extreme environments on the entire planet. Quantum chips are kept inside these huge, wild-looking refrigerators that cool them down to just a tiny fraction of a degree above absolute zero. That is colder than the empty vacuum of deep space. But even with all that crazy protection, errors still happen. And that's why the real genius here The real breakthrough is something called quantum error correction. It's this brilliant system that uses extra helper qubits to constantly check on the main ones, find any errors, and fix them in real time, all without ever actually looking at the main calculation and causing it to collapse. It's like a perfectly choreographed relay race for information. So why? Why are we going through all this unbelievable trouble? Why build these incredibly complex, fragile, and expensive machines? Well, because the problems they promise to solve will completely reshape our world. Just take medicine, for example. We could design new life-saving drugs in just a few months instead of decades, because we could perfectly simulate how they'll interact with our bodies. We could finally get to the bottom of diseases like Alzheimer's. We could even model new viruses and stop the next pandemic before it even has a chance to start. And for physics, we could simulate what goes on inside a black hole, or finally figure out what dark matter actually is. We could design completely new materials for things like clean energy or space travel. We might even be able to sift through all the noise of the cosmos and find a signal from an alien civilization. But maybe the most powerful impact of all will come when we pair quantum computing with artificial intelligence. The insane processing power of quantum could train AIs on a level we can barely even imagine, creating this incredible feedback loop where each technology makes the other one smarter and faster, over and over again. Of course, a power like this is a massive double-edged sword. As the pioneers in this field are quick to warn us, the potential for things to go wrong is, well, it's enormous. We have to move forward with both incredible ambition and extreme caution. So just think about our journey. For thousands of years, we've been manipulating matter to help us calculate things. And we peaked by teaching silicon, basically a rock, how to think. Now we are right on the verge of teaching the fundamental atoms of reality themselves how to dream. The only real question left is, what are we going to ask them to dream of first?